Welcome back to Algebra 2, Chapter 13, Section 2 in this book. And we've been talking about trigonometry. Don't we feel smart? Alright, so this is called General Angles and Radian Measurements. Now, first idea I want to tell you is there is a relationship between the triangles we've been studying with trig, these right triangles, and circles. And this is what it is. If I draw a radius from the center of my graph that's got a circle on it, and I go up till I hit the side of the circle and drop it down, I have put a right triangle inside the circle. So we will be expanding on that idea a little bit. Now the other thing is, do you remember what the quadrants are numbered? 1, 2, 3, 4. By tradition you go around counterclockwise. The symbol for counterclockwise is CCW. And by tradition in Roman numerals, that's why you had to learn them in 3rd grade, just for this moment. Now, the degrees that you would measure the degrees of theta, and the starting point is this positive x-axis, and this is considered 0 degrees. If you go up here, you've gone to 90, over here 180, down here to 270. So the first thing that they always have you do when you get to this point is think about that if it wasn't triangles, if you're just sweeping around circles in this piece of graph paper, then what would they be measured? So this angle is 210, so we start at 0 and we go to 90, 180, and a little bit more, and there is the end of it, the terminal where it terminates. And that is what a 210 degree angle would look like. Also, it can be described as that we have gone down 30 degrees from the x-axis. So, or 30 degrees down from 180, because 180 is over here. Sometimes it has a negative. If it has a negative, instead of going our regular counterclockwise, we go clockwise. So if it's negative 45, you just go down 45 degrees from our 0 point. And this one is 510. So you start it at 0 and you go all the way around one time, that's 360, and then you add another 150, and this would terminate over here. And it's actually at the same place as if we had just started right here and gone around 150. So these two are said to be coterminal. Fancy math talk for it, they end at the same place. Alright, so take a look at those, make sure you understand them in your book. Okay, here's another idea. Circle thetas can be measured in degrees or radians. Now, what does that word mean, radians? When I taught public school, I had to teach this in the physics classes I taught also. And I kept this little red piece of yarn in my desk just for this moment. So imagine the red piece of yarn, and I take it out, and I lay the red piece of yarn down on my circle, and it's the same exact length as the radius. Got it? Then I take my piece of yarn and I see how many times I can stretch it around the circle. And it goes 1, 2, 3.14159. What number is that? 3.14159 on forever. What is that number? It's pi. That's where pi comes from. It's how many times you can put the radius around half a circle. If you go all the way around the circle, you go 2 pi times. So one circle is 2 pi radians, a half a circle is pi radians. Okay? So radians are another way to measure. Now, this leads us to a thing that I call the trig circle. It's up here. It's written out more in your book, but this is the idea. That you could measure 90 degrees in degrees, or it is halfway around to pi, so it's pi divided by 2. You could go all the way around to pi, and you can measure it as 180 degrees or pi radians. This is pi over 2 radians. We could go all the way down to here, and that's either 270 degrees or 3 pi over 2 radians. Now, they used to make you memorize this circle, and I think for my boys in college they made them do it again. I know Nathan did, but I'm not sure if Eli has had to memorize it or not. But it was part of that whole thing that people didn't have calculators, so they would do a lot of their trig work using the Trig Circle and using those common triangles. But now we have calculators, so I think it's kind of dumb, but don't quote me on that. All right, so sometimes you have to convert. You're given degrees and you need radians, or you have radians and you need degrees, and this is the conversion factor. 180 degrees is the same thing as pi radians. Your calculator, even though we're talking about radians now, it still needs to be in degrees to do these problems. Later on, there are some problems that the calculator will need to be in radians for. Not yet. Keep it in degrees. Okay, so here's my problem. Convert 110 degrees to radians. So I write down what I was given, 110. I write my conversion factor with the degrees I have in the denominator because I want them to cancel out, and what I want to change it to in the numerator. And then I write the relationship, the numbers that go with them. 180 is the same thing as pi radians. Pi is a number. So these degrees cancel out, and I'm left with radians. You multiply any number on top, dividing one on bottom. So it's 110 times pi divided by 180. That reduces to 11 pi over 18, which is really considered the answer because it's not rounded. But if you want to know what that is, because nobody knows what that is 1.92 radians. Okay, here's another one. This time we have radians, negative pi over 9 radians, and we want to convert it to degrees. So we first start with what we know, what we're given. Pi is in the numerator, 9 is in the denominator. Put the units of what you're given in the numerator and the units you want to get rid of in the denominator and the units you want to change it to in the numerator. Then write the math relationship. 180 is the same thing as pi. The pi radians, the whole thing cancels out. We're left with negative, understood negative 1 times 180 divided by 9, and that's negative 20 degrees. Okay, this also came from geometry. We learned about Pac-Man and roly-poly-oly. It's Grandpa. He's roly-poly-oly. He's short and square and round. All right, you'd have to watch the show. It's the early 90s thing, Disney Channel. All right, so this is Pac-Man. That means the hinge of his jaw is in the middle of his head. So this angle theta is the same as the sector angle, as long as it's an angle. But we can also measure the length of this dotted line, like in centimeters, and that is S. That is called the sector length, and it is abbreviated S. Okay, so here's our formula. The arc length S, the length of that dotted line, is equal to the radius, either side, either his upper mouth or lower mouth, times theta in radians. The area of the sector, if we wanted to color in his mouth and see how big of an area we colored, it's 1/2 the radius squared times theta in radians. So here's an example. We have a theta of 60 and a radius of 9. They want the sector, the length of the arc length and the area of the sector. So first we need to convert our 60 degrees to radians. So degrees cancel out, and we do 60 times pi divided by 180. It's pi over 3 radians. So now radius times this theta is 9 times pi over 3. It was 3 pi, which is about 9.42 centimeters. I think I drew it about the scale. Okay, and if we want the area of the sector of his mouth, it would be equal to 1/2, go back to our formula, times the radius 9 squared times the theta in radians. So 1/2 times 9 squared over pi over 3 is 27 pi over 2, which is about 42.4, and that would be centimeters squared if this one is centimeters. Because remember, areas are squared. Alright, I think this is fun and interesting, and you look mighty smart knowing this, talking about thetas and radians and arc lengths. So, come back and we'll do some more trig. Math is great.